Let's review a few common parametrizations of curves in the plane, just so that we remember how to write them down. None of these are like tricky parametrizations, but they are very common. And so it will be nice if we have sort of easy mental access to these parametrizations so that we can write them down without having to think too hard about it. So the first one is parametrizing a line segment. So if we want to go from a point P to a point Q, okay, and we want to parameterize a line segment that goes from P to Q, the easiest way to write down this parametrization is so that we're at P when T is 0 and we're at Q when T is 1. And the way to do this is just to write down the point that you want to start at plus T times the vector from P to Q, right? And if you want to start at P, then start at P. So P plus T times the vector going from P to Q. And remember, the vector going from P to Q, that's just your end point minus your start point, right? So, if we wanted to go, if P were 1, 2, 3, and Q were -4, 7, whatever, 2, okay, then P minus Q, or Q minus P, so -4, -1, that'd be -5, and then 7 minus 2, that would be +5, and then 2 minus 3, that would be -1. And then we could write down our parametrization. So P is 1, 2, 3, plus T times -5, 5, -1. Okay, so parametrizing a line segment, as long as you know where you want to start and what direction you want to go in, parametrizing a line segment is very straightforward. Notice that when we plug in t equals 0, we do just get this point that we started with, so that's P. And when we plug in t equals 1, we get P plus 1 times the vector from P to Q. But if you start at P and you add the vector from P to Q, you get the point Q. So as I claimed, this is a parameterization that is at P when t is 0 and is at Q when t is 1. Another very common curve to have to parameterize is a circle. So let's parameterize a unit circle that goes counterclockwise around the origin. Right? Remember, writing a parameterization is essentially writing a vector-valued function that traces out that shape. So since we're working in a plane here, I just need to write down what is the x-coordinate function and what is the y-coordinate function. And they're both going to be functions of some parameter, which I'm calling t. Fortunately, for parameterizing a unit circle around the origin going counterclockwise, we have functions that do that. Cosine t and sine t. That's essentially what sine and cosine are for. That's not the only way to define them, but from a certain point of view, this is the meaning of sine and cosine. Of course, we can check that this does stay on the unit circle just by verifying that the magnitude of this is always 1, which amounts to the fact that cosine squared plus sine squared is 1. So this parameterization does do what we want. It goes around the unit circle, around the origin, and it does go counterclockwise because if you just think about where we're starting, when t is 0, we're at the point 1, 0, right? Because cosine of 0 is 1 and sine of 0 is 0. And as t increases, so when t increases, cosine gets smaller and sine gets bigger, and so we go this way. And so that means we are going counterclockwise around this unit circle. Okay, of course that's just the unit circle. We will need to parameterize all kinds of other circles. So for a little variety, let's parameterize a circle with radius 4, centered at -2, 3, that goes clockwise, starting at 2, 3. So -2, 3 is up here. -2, 3 up here. So there's our center. And we want to start at 2. Actually, I don't want to start at 2, 3. Sorry. I want to start at -2, 7. That's where I want to start. So that's going to be up here. So this is our starting point, and we want to go clockwise, so that's this way. So there are lots of points of view on like how to come up with a parametrization for this. They all give you equivalent results in the end, but here's one way of thinking about it. So, so let's start with cosine and sine. Right? Those are our basic circle drawing functions. Okay, put our parameter in here. So this, as it stands, this would parameterize a unit circle, centered at the origin, going counterclockwise. To make the radius 4, we just need to scale this whole thing up. So let's multiply both of these by 4. Right, so now the radius is 4, and you can check that if you calculate the magnitude of this vector, you do just get the constant 4. It turns out it is not doesn't depend on t. Okay, well this is centered about the origin. To get it to be centered at -2, -3, well, we just need to shift where this where this is happening. So instead, right now it's centered at x equals 0. We want it centered at x equals -2. So just subtract 2 from your x coordinate, and by the same token, add 3 to your y coordinate. So now it's centered around the point that we want it to be centered around, but if we just plug in t equals 0 now, right, cosine of 0 is 1, so we get 4 minus 2, that's 2, and sine of 0 is 0, so 4 times 0 plus 3, that's 3. Okay, so we aren't starting at -2, 7 the way we have it written. We're actually starting over at this right-hand point. Right? So what can we do? Well, what we need to do is sort of add an initial angle. T is basically playing the role of the angle that the point makes with the horizontal, and we want our angle to start at pi over 2. So let's just add pi over 2 right here. Okay, so that's going to change what we get when t is equal to 0. So now when we plug in t equals 0, we get 4 times cosine of pi over 2, but cosine pi over 2 is 0, so 0 minus 2, we get -2. And then when t is 0, we get 4 times sine of pi over 2, that's 1, so 4 times 1 is 4, plus 3 is 7. Okay, so you can see this adding an initial angle let us start up here at the top of the circle instead of at the right-hand point on the circle. Okay, now let's think about what direction we're going. Now as t increases, this angle is getting bigger, and so cosine continues getting negative. So this coordinate is decreasing as t increases. So as t increases, from 0 I mean, cosine decreases, and as the angle gets bigger than pi over 2, sine also decreases. So that means we're going to go this way. Well, that's not the way we wanted to go. We wanted to go clockwise, not counterclockwise. And there's an easy way to fix this. Just reverse time, right? If going forward in time sends you counterclockwise, then reversing time will send you clockwise. And the way to reverse time is just to stick a minus sign in front of t. So this is a parametric curve that parametrizes this particular circle. Notice one thing that we haven't said about this parametrization is how fast it's going around the circle. And that's if all we want to do is trace out the circle and we don't care about how fast, then this will work. If we do care about how fast, well then we have to worry about what number we stick in front of the t here. The minus sign is there to get us going in the correct direction, but if we stick a 2 in there, it'll go around faster, and if we stick a 1/2 in there, it'll go around slower. Fortunately, for our purposes, for what we are going to need parametric curves for, it turns out how fast we traverse the curve doesn't actually matter, so let's not worry about it. The last common parametrization is parametrizing a graph. So let's parametrize the graph of a function. Now this is, right, if we have some function from x equals a to x equals b, well, we actually have a parametrization built in, right? Because if x is x, what does y have to be? Well, to be on the graph, y has to be f of x. And so there's your parametrization, done. If you find it confusing to use the variable x as a parameter, when also there's a coordinate called x, you could call it t instead of, call the parameter t instead of x, and that would give you t comma f of t. Okay, so if you want to parameterize a graph, it comes with a parameterization sort of built in.